Now let's talk about how you find the steady state using graphical methods. What I'm going to do in the first method is essentially just reproduce the analysis that we did using Excel, except we'll now do it using a graph. So we'll call this method 1. And what method 1 is going to exploit is this law of motion for capital, which says that capital next period is equal to 1 minus delta divided by 1 plus n times kt plus s times z divided by 1 plus n times kt to the alpha. Well, now we can think about this in a graph where you have kt on one axis and kt plus 1 on the other. So let's call this kt, and up here we'll have kt plus 1. And what we'll put here is a 45-degree line. And what this is going to represent, if we plot this, is there's going to be this linear portion which then just gets added to this concave part. And you end up with something that looks like that. Okay? So this is that whole shebang. It is 1 minus delta, 1 plus n kt plus sz, 1 plus n kt to the alpha. Now the key here is that the steady state is going to be where kt equals kt plus 1, and that's then just what we call kss. What the 45-degree line does is it tells us exactly the point at which kt is equal to kt plus 1. So we know that the steady state occurs there. In our spreadsheet, that was the point that we converged to when you copied the formulas down the spreadsheet and you saw that k got, the changes in k got smaller and smaller and smaller until they were 0. Sorry about that. Okay, so then the question is, how do we do the analysis? Like, suppose that you start, let's go with another color now. Suppose that you start at an initial k below the steady state. Then what we know is that the value of kt at that point is less than the value of kt plus 1. So kt plus 1 is bigger than kt. You then reflect that back over here. That gives us what k1 is. Then k1 gets converted into k2. Reflect that back over here, tells us what k2 is. And you can see that this process is going to continue until each incremental change in k, you can see here the incremental change in k, gets smaller and smaller. And so the dynamics of the model are such that if you start at a point that is below the steady state, you will ultimately converge to this steady state. And then analogous reasoning applies if you start at a point above the steady state, except that at that point, because you're above the steady state, you're going to converge down to the steady state over time. And it'd be useful for you to draw this graph on your own and convince yourself of that. So that's method 1, graphical method 1 for determining the steady state.